Hi, I'm Joyce, and my final project for this course is about depth sensing with linear polarizing filters. My project implements a 3D reconstruction pipeline using a camera equipped with the filter, and then I take photos of different objects with different filter angles, and then I process them in Python to calculate the normals and obtain depths. So this method yielded the best results with dielectric objects that have more angled and irregular surfaces compared to those with smooth and flatter surfaces. So first, we'll go over some of the motivation behind this topic. In class, we learned about 3D reconstruction using photometric stereo, and more specifically, in Assignment 5, we got to implement both calibrated and uncalibrated photometric stereo. Since I didn't really have any professional equipment, I found it a bit challenging when trying to shine light on my objects at different angles while also trying to take photos at the same time. So, in contrast to the different lighting angles and the inversion surfaces that photometric stereo requires, depth sensing with linear polarizing filters just need dielectric surfaces and regular rotations of the linear polarizing filter on our camera between photos. This seemed like a much more manageable workflow for one person to implement, and I thought it would be cool to try it out. So the structure of this project is inspired by the articles Depth Sensing using geometrically constrained polarization normals and Detached shadow constrained shape from polarization. These articles definitely go more in depth than the scope of this project, but the formulas that they list for the calculation of azimuth and zenith angles, as well as their relationship with surface normals, were very useful in the coding implementation of my project. So I started off by implementing my image processing pipeline in Python. The main idea behind 3D reconstruction using linear polarizing filters is that when light reflects off of surfaces, it can become polarized, which a linear polar filter rotated at different angles can extract information from, as the polarized light aligns with the different rotations of the filter. So this information, which is encoded in the azimuth and zenith angles, can then be used to calculate the surface normals, which we can use for 3D reconstruction. On a quick note, the azimuth angle defines tilt in relation to the plane of the image, and the zenith angle defines the tilt of the surface normal with respect to the camera. So our first equation here describes the intensity at a specific image point, and we can see that Imax and Imin represent the maximum and minimum intensities of the overall image respectively. We also know the rotation angle phi pol for each image that we capture, so we would be able to use the formula to find the azimuth angle for different image points by just taking inverse operations. Then we define the degree of polarization rho, which we use to help estimate the zenith angle. The articles describe a relationship using the Fresnel equations, but for the purposes of this project, we assume a simpler model. And after finding the azimuth and zenith, we're able to obtain our surface normals using this relationship with the normals here. And finally, we get our depths by integrating our normals. So after getting the code roughly implemented, I started taking photos, and it's just really important to make sure that the only change between the photos of each object is the angle of the linear polarizing filter. The articles share that two azimuth angles shifted apart by pi radians are indistinguishable in polarized images, so I chose to take 4 photos at filter rotations of 0, 45, 90, and 135 degrees. So apart from the filter angle, everything else I kept the same throughout the images for each object. My camera was set in manual mode, put in a fixed position, and tethered to my computer. The objects remained in the same position throughout the 4 photos, and I had this LED desk lamp that I shined on the object at a constant angle and brightness level. Also, since my images were captured in RAW format, I also had to do a bit of pre-processing before putting them through my code pipeline. I used dcrawl to convert them into linear 16-bit RGB images in .tiff format, and also got rid of unwanted background by writing a script to crop my images based on user-defined top left and bottom right points of a rectangle. Here are some of my results. First, I have this Rubik's Cube. You can see the azimuth, zenith, and normals. And here we have the depth map and some different angles of the 3D reconstruction. This had the shell and this origami ball thing. And finally, I have this mug. And as you can see, my process worked a lot better on the dielectric objects that had more edges and differently angled surfaces, like the Rubik's Cube and the shell, in comparison to the mug, which had like smooth and flat surfaces. And we can see that more future work could definitely be done on trying to make my process work better for these smoother and flatter surfaces. I think it would also be interesting to experiment with other types of lens filters and potentially combine them with linear polarizing filters to see what kind of results we might see. And here are my references. Thank you for watching.